May 24th, 1876. Brooklyn Bridge construction site. The engineering consensus from European bridge builders would never fully capture what they witnessed that morning. American workers, wrapping steel cable with galvanized wire using methods that contradicted everything European masonry traditions said was necessary for lasting construction. Through the salt spray and industrial smoke of New York Harbor, 1,500-foot spans rose with protective systems that seemed excessive to European observers. No stone archways, no proven centuries-old techniques, no trust in time-tested materials. Yet they were building bridges with longevity that European stone structures could not guarantee. In European engineering, massive stone towers required decades to prove their worth. Each bridge was essentially custom masonry, different quarries, different mortar, different weathering patterns. Most carried weight limits that restricted heavy traffic. The Americans were operating with protective philosophy the Europeans had dismissed as wasteful. Hot dip galvanizing, multiple barrier layers, sacrificial zinc coatings. Protection systems that added cost but promised century-class service life. 3,000 miles from European workshops, the most decisive corrosion prevention breakthrough in bridge history was revealing itself. Not in superior stone, not in thicker steel, but in the systematic zinc protection that would shield every American wire in ways European tradition never imagined necessary. The morning wind off the East River carried more than salt spray. It carried doubt. Washington Roebling stood at the edge of the Brooklyn construction yard, telescope in hand, watching his crews position another section of tower masonry while the critics' voices echoed in his memory. Wire rusts. Masonry lasts. The refrain had followed him through every engineering society meeting, every funding discussion, every newspaper interview since his father's death had thrust him into the chief engineer's chair. The numbers told a different story, but numbers required faith that few possessed. 1,595.5 feet between towers, longer than any suspension span ever attempted. 276.5 feet of granite and limestone rising from bedrock, each stone cut to tolerances that would make European cathedral builders proud. But the real audacity lay in what couldn't be seen yet. Cables 15 3/4 inches in diameter, each containing 5,282 individual wires. Every strand galvanized in molten zinc before a single twist was spun. Roebling folded his telescope and walked toward the wire testing station where samples from the latest shipment awaited inspection. The Bessemer steel debate raged in engineering circles, some swearing by the new process for its consistency, others preferring crucible steel for its proven strength. But Roebling's specification demanded something more fundamental. Every wire, regardless of its steel ancestry, must emerge from a zinc bath heated to 850 degrees Fahrenheit. The molten metal would bond with the iron atoms at the surface, creating an alloy layer that served as the first barrier against the maritime environment that would assault this bridge for decades to come. The marine spray posed the greatest threat. Chloride ions from seawater could penetrate the smallest crevice, and when moisture followed, the electrochemical dance of corrosion began its relentless work. Add the coal soot from steamships and locomotives, the freeze-thaw cycles that cracked protective coatings, and the simple passage of time, and most metal structures surrendered within a generation. Roebling's answer was not hope, it was process. Each wire would receive its zinc armor before joining the cable. No shortcuts, no post-assembly coatings that left gaps at contact points. The hot dip galvanizing process created a metallurgical bond that couldn't be painted on or brushed over. When the zinc finally succumbed to corrosion, it would sacrifice itself to protect the steel beneath, buying decades of service life that thin coatings couldn't match. The critics understood none of this. They saw the additional cost per ton, the delays while contractors perfected their galvanizing techniques, the complexity of specifying coating weights measured in ounces per square foot rather than simple yes or no decisions about protection. European engineers, veterans of cast iron bridges and stone arches, questioned whether American ambition had finally exceeded American capability. but Roebling had studied the chemistry. Zinc's sacrificial nature meant that even when the coating developed microscopic breaks, the surrounding metal would continue protecting the steel substrate. The electrochemical series guaranteed it. Zinc would always corrode before iron, creating a cathodic protection system that worked at the molecular level. This wasn't engineering optimism. This was metallurgical certainty. The funding pinch arrived with autumn. Municipal bonds required voter approval, and voters listened to newspaper editorials questioning whether wire cables could match the permanence of European stone bridges. The Brooklyn Bridge would cost more per foot than any structure in American history, and every additional specification, like mandatory galvanizing, represented dollars that skeptics could identify and attack. Then Washington's health began failing. The caisson disease, contracted during his supervision of the underwater foundation work, left him weakened and often confined to his Columbia Heights home. Critics seized on his absence from the construction site as evidence that the project lacked proper leadership. Wire rusts, they repeated. Masonry lasts. American ingenuity meant nothing if American management couldn't maintain consistent oversight. Emily Warren Roebling stepped into the gap with characteristic precision. She carried Washington's directives to the site each morning, translated his technical decisions into work orders, and returned each evening with progress reports and questions that required his engineering expertise. The system worked, but it required explaining to trustees, contractors, and newspaper reporters who had never encountered a woman managing construction logistics on this scale. The material debates deepened as winter approached. Bessemer steel offered consistency and cost advantages, but crucible steel provided the certainty that came from centuries of proven performance. The galvanizing specification remained non-negotiable. Every wire must receive its zinc coating before installation, but contractors pushed for alternatives that would reduce the complexity and cost of their bids. Roebling's answer remained constant: process, not promises. The wire specification called for tensile strength approaching 160,000 pounds per square inch, but strength meant nothing if corrosion reduced the effective cross-section year by year. The zinc coating, measured at approximately 1 ounce per square foot minimum, would provide the time that strength alone could not guarantee. If the zinc failed, the bridge failed. Not immediately, steel possessed remarkable strength even when surface corrosion began, but inevitably. The mathematics of deterioration were as predictable as the mathematics of load distribution. Thin coatings might satisfy initial inspections, but they couldn't satisfy the decades of service that the city deserved for its investment. The traveler system awaited completion, ready to carry workers and wire across the span thousands of times as the cables took shape. Each pass would add 4 wires to the growing bundle, and each wire carried its protective zinc armor into a structure designed to last beyond the lifetime of everyone who would witness its construction. The critics' voices still carried across the construction yard, but the numbers were beginning to align with the doctrine. American ingenuity would prove itself not through grand gestures, but through the systematic accumulation of protected steel wire, one galvanized strand at a time. The wire arrived at the Brooklyn yard in massive spools, each strand already bearing its zinc armor from the contractor's galvanizing works. Roebling examined the first delivery through his magnifying glass, noting the characteristic crystalline surface that indicated proper hot dip processing. The zinc hadn't been painted on or electroplated. It had been alloyed into the steel's surface through the molecular violence of molten metal meeting iron at 850 degrees. This was mechanism, not myth. Corrosion followed predictable electrochemical rules, and Roebling treated it as a logistics problem. Keep water out, and when water inevitably penetrated the outer defenses, feed the corrosion process with zinc instead of steel. The strategy required multiple barriers working in sequence, each layer buying time for the next. The galvanizing bath created the first barrier. When the wire entered the molten zinc, iron atoms at the steel surface bonded with zinc atoms to form a tough intermetallic layer. This wasn't a coating that could chip off. It was a metallurgical transformation that made the outer surface of the steel wire into something new. The zinc-iron alloy possessed different electrical properties than pure steel, creating a sacrificial anode that would corrode preferentially even if the pure zinc topcoat developed microscopic breaks. Emily Roebling stood beside the testing station as crews measured coating weights on sample wires. The specification called for approximately 1 ounce of zinc per square foot of wire surface, translating to a coating thickness of roughly 1 7/10 miles. Modern structural wire often carried 3 ounces per square foot, yielding coatings exceeding 5 mils thick. The mathematics were unforgiving. Life tracked thickness, and thickness cost money that had to be justified to trustees who measured success in dollars per foot of completed bridge. The spinning operation began with mechanical precision that impressed even the European observers who had come to witness American engineering methods. The traveler system carried wire across the completed span in continuous loops, building each cable strand by strand through thousands of individual passes. 4 wires traveled with each crossing, and workers positioned them according to patterns that would create a circular cross-section when compaction began. Roebling watched through his telescope as the traveler made its methodical journey from Brooklyn to Manhattan and back. The system eliminated the need to splice short wire segments into longer cables, creating continuous steel strands that ran the full distance between anchorages without breaks that could concentrate stress or trap moisture. Each wire maintained its galvanized protection from anchorage to anchorage, a single piece of protected steel contributing to the cable's collective strength. The compaction process required different mathematics. As workers positioned hydraulic presses around the growing cable bundle, the circular cross-section began to emerge from what had been a loose collection of individual wires. The pressing operation squeezed air gaps out of the bundle while maintaining the zinc coating on each strand. Excessive pressure could damage the galvanizing, but insufficient compaction would leave voids where moisture could accumulate. The second barrier began taking shape as crews prepared the wrapping wire. Number 9, soft galvanized wire arrived in smaller spools, each strand carrying its own zinc coating, but specified for different duty than the structural cables. This wrapping wire would spiral around the compacted cable under tension, creating a helical skin that eliminated gaps where water could penetrate to the structural strands beneath. The wrapping machines crawled along the suspended cables like mechanical spiders, laying the protective wire in precise overlapping spirals. Each turn had to maintain consistent tension. Too loose and gaps would develop. Too tight, and the wrapping wire might break or damage its own galvanized coating. The operators worked with measuring wheels that counted turns per foot, ensuring uniform coverage that would resist wind-driven moisture for decades. As the wrapping progressed, crews followed with red lead paste, bedding each spiral of protective wire in a mixture that would seal microscopic gaps and provide additional corrosion resistance. The paste required careful application, enough to fill voids without creating thick layers that could crack and admit water. Workers used brushes and spatulas to work the red lead compound into every crevice between wrapping wire turns. The mathematical reality of coating thickness became visible in cross-sections of test samples. Heavy structural galvanizing, applied through batch hot dip processing, created thick alloyed layers that could resist decades of exposure. The multiple ounce coatings common in 1870s, bridge construction contrasted sharply with modern practice, where continuous galvanizing lines and electrolytic processes prioritize smooth surfaces and fast throughput over maximum thickness. Batch processing moved slowly but built substantial protection. Each wire spent extended time in the molten zinc bath, allowing the iron zinc alloy layer to develop fully while pure zinc accumulated on the surface. The resulting coating possessed both the bonded durability of the intermetallic layer and the sacrificial protection of the zinc topcoat. Time in the bath translated directly to coating thickness, and thickness translated to service life measured in decades rather than years. The third barrier emerged as paint crews followed the wrapping operation with lead-based coatings. Multiple coats built a weatherproof skin over the red lead paste and wrapping wire, creating an outer shell that would shed water and resist atmospheric corrosion. The paint system worked in conjunction with the galvanized barriers beneath, not as a replacement for zinc protection, but as an additional layer that extended the time before moisture could reach the galvanized surfaces. Workers moved along the cables with brushes and spray equipment, applying each coat according to specifications that defined coverage, thickness, and curing time. The lead-based formulations provided superior durability compared to modern alternatives, creating a tough skin that could flex with thermal expansion while maintaining its protective seal. Each coat had to cure completely before the next application, slowing the work, but ensuring proper adhesion between layers. The cable system began resembling a sealed pressure vessel designed to exclude air and moisture from the structural steel within. The galvanized main wires provided sacrificial protection at the steel surface. The galvanized wrapping wire eliminated gaps where water could penetrate. The red lead paste filled microscopic voids. The multiple paint coats shed atmospheric moisture and resisted chemical attack from industrial pollutants. Engineering joy emerged from numbers aligning with doctrine. Each barrier performed its assigned function while working in combination with the others. The system didn't depend on any single protective mechanism. It created redundant defense that could survive the failure of individual components while maintaining overall integrity. The mathematics of corrosion rates, coating thickness, and barrier performance converged into a cable design that could outlast the careers of everyone involved in its construction. The inspector's report landed on Washington Roebling's desk like an artillery shell. Wire samples from the latest delivery had failed tensile testing, yet somehow identical spools had already been incorporated into the cable spinning operation. The mathematics were stark. If substandard wire comprised any significant portion of the structural cables, the bridge's safety factor could drop below acceptable limits. The difference between a bridge that carried traffic safely and one that collapsed under load might rest in metallurgical deception that threatened to unravel years of meticulous engineering. J. Lloyd Hayes' wire manufacturing operation had built its reputation on volume and political connections rather than metallurgical excellence. His contracts with the bridge trustees reflected competitive pricing that other suppliers couldn't match, but the economics of wire production followed unforgiving rules. High-grade steel required expensive raw materials and careful temperature control during drawing. Proper galvanizing demanded time in molten zinc baths and precise coating weight specifications. Shortcuts in either process could reduce costs dramatically while creating wire that looked identical to properly manufactured material. The fraud revealed itself through systematic inspection that Roebling had insisted upon despite protests about delays and additional expense. Random sampling of wire deliveries showed tensile strengths varying wildly from specified minimums, while microscopic examination revealed galvanized coatings that appeared substantial but measured below specification thickness. Hayes' operation had apparently been substituting rejected wire into accepted deliveries, counting on the probability that individual strands would never be tested once incorporated into the massive cable bundles. Emily Roebling coordinated the investigation with characteristic precision, organizing crews to examine cable sections that had already been spun while documenting the extent of compromised material. The timing created a nightmare scenario. Thousands of wires had been positioned and compacted before the fraud was discovered. Removing and replacing individual strands would require dismantling cable sections and respinning portions of the Traveler operation, consuming months of progress and threatening the project's financial viability. Washington's response emerged from engineering calculation rather than emotional reaction. The safety factor had been designed to accommodate exactly this type of contingency, not fraud specifically, but the inevitable reality that real-world construction never achieved theoretical perfection. The original specification called for 5,282 wires per cable, creating a safety factor exceeding 5 when calculated against maximum expected loads. If Hayes' substandard wire reduced effective strength by a measurable percentage, additional wire could restore the margin without redesigning the entire cable system. The mathematical solution was elegant in its simplicity. Add 150 wires to each cable at Hayes' expense, maintaining the required safety factor despite the compromised material already in place. The additional wire would be sourced from reliable suppliers and subjected to enhanced inspection protocols that eliminated any possibility of further substitution. The work could proceed without dismantling completed sections, but Hayes would bear the full cost of materials and installation for the remedial wire. Crews mobilized to implement the fix with mechanical efficiency that impressed even skeptical trustees. The Traveler system resumed its methodical crossings, carrying additional wire that would be distributed throughout the cable cross-section to ensure uniform strengthening. Each new wire carried its galvanized protection according to the original specification, creating redundant strength that compensated for the metallurgical uncertainty introduced by Hayes' deception. The political implications rippled through New York's engineering community and municipal government. Bridge construction represented the largest public works investment in the city's history, and any hint of contractor fraud threatened public confidence in the project's management. Newspaper editorials questioned whether adequate oversight existed to prevent similar deceptions in other aspects of construction, while rival contractors accused each other of similar practices. Roebling's reputation for technical competence provided crucial stability during the crisis. His systematic approach to inspection and specification had detected the problem before it could compromise structural integrity, and his solution demonstrated the value of conservative safety factors in real-world construction. The additional wire requirement served as both punishment for Hayes' deception and advertisement for Roebling's engineering judgment. The schedule pressure intensified as autumn approached. The last wire run was scheduled for October 5, 1878, creating a deadline that allowed no margin for extended delays. Every day spent investigating wire quality or implementing remedial measures pushed completion closer to winter weather that could halt critical operations. Ice formation on the cables would make wrapping and sealing operations impossible, potentially forcing a shutdown until spring thaw. Work crews adapted to the enhanced inspection protocols without significant delay. Each wire delivery now underwent tensile testing of multiple samples, microscopic examination of galvanized coatings, and dimensional verification that confirmed adherence to specification requirements. The additional steps consumed time but eliminated the possibility that substandard material could enter the cable system undetected. Hayes' response revealed the contractor's priorities with uncomfortable clarity. Rather than accepting responsibility for quality control failures, his representatives argued that the bridge specification exceeded industry standards and that minor variations in wire strength were acceptable within normal construction tolerances. The position ignored the fundamental mathematics of suspension bridge design. Cable strength determined load capacity directly, and load capacity determined public safety. The trustee board faced pressure to terminate Hayes' contract entirely, but the legal and logistical complications of changing suppliers during active construction threatened delays that could prove more costly than the wire fraud itself. The compromise solution required Hay to provide additional wire at his own expense, while submitting to enhanced inspection protocols that eliminated his ability to substitute materials without detection. Emily Roebling's daily site visits took on additional importance as the remedial work proceeded. Her presence ensured continuous communication between Washington's technical oversight and the field operations that implemented his directives. The fraud investigation had demonstrated the necessity of systematic inspection, but it had also revealed the effectiveness of the management system that had detected and corrected the problem before structural damage occurred. The additional wire installation proceeded with clockwork precision that vindicated the original cable design. Each strand found its designated position within the growing bundle, contributing to collective strength that exceeded the original specification despite the presence of compromised material. The safety factor remained above 5, providing the margin that would allow the bridge to carry loads safely for decades beyond its design life. October 5th arrived with the final wire run completed according to schedule. The Traveler system made its last crossing, delivering the wire that would complete the structural cables according to the revised specification. The fraud crisis had been resolved through systematic engineering rather than legal battles, proving that numbers and specifications provided more reliable protection than contracts and promises. The compaction was complete. 5,432 wires now formed a solid cylinder of steel 15 3/4 inches in diameter, each strand maintaining its galvanized protection while contributing to the collective strength that would carry the bridge deck for generations. The hydraulic presses had squeezed air gaps from between individual wires, creating a dense bundle that resembled a single massive cable rather than thousands of separate strands. The clamping operation began at dawn with mechanical precision that had been rehearsed through months of preparation. Cast iron clamps, each weighing several tons, were positioned around the compacted cable at precise intervals along its length. These clamps would distribute the enormous tension loads from the suspended deck structure across the entire cable cross-section, preventing individual wires from carrying disproportionate stress that could lead to fatigue failure over decades of service. The wrapping machines arrived on schedule like mechanical spiders preparing to cocoon their prey. Each device crawled along the suspended cable under its own power, carrying spools of soft galvanized number 9 wire that would form the second barrier in Roebling's protective system. The machines maintained consistent tension as they laid down spiraling wraps, overlapping each turn to eliminate gaps where moisture could penetrate to the structural cable beneath. Emily Roebling watched the first wrapping machine begin its methodical journey across the East River span. The device moved at walking pace, its mechanical arms guiding the galvanized wire in precise helical patterns around the cable circumference. Measuring wheels counted turns per foot to ensure uniform coverage, while tension gauges maintained the precise force needed to compress the wrapping wire against the cable surface without breaking the protective zinc coating. The red lead paste followed immediately behind the wrapping operation, applied by crews who worked with brushes and putty knives to bed each spiral wire turn in the protective compound. The paste filled microscopic gaps between wrapping wire turns while providing additional corrosion resistance through its lead oxide chemistry. Workers had to maintain consistent coverage without creating thick layers that could crack under thermal expansion, a balance that required experienced judgment about paste consistency and application thickness. The mathematics of the protective system became visible as the work progressed. Each turn of wrapping wire overlapped its predecessor by precisely calculated margins that eliminated linear gaps where water could penetrate. The red lead paste bonded chemically with both the galvanized wrapping wire and the galvanized structural cable beneath, creating a unified barrier that functioned as a single protective layer rather than separate components that might separate over time. Washington observed the operation through his telescope from the Columbia Heights house, noting the systematic progress that transformed his specifications into physical reality. The wrapping operation represented the critical transition from individual wire protection to complete cable sealing. Once the helical wire skin was complete and bedded in red lead paste, the structural cable would become effectively isolated from atmospheric moisture, except at the anchorage points where special sealing details would complete the protective envelope. The paint crews organized their materials according to specifications that defined coverage rates, thickness requirements, and curing times for the lead-based coating system. The first coat would be applied directly over the red lead paste and wrapping wire, penetrating into surface irregularities to create maximum adhesion. Subsequent coats would build thickness and weather resistance, with each layer allowed to cure completely before the next application. The lead-based paint formulations provided durability characteristics that modern alternatives couldn't match. The metallic lead particles created a dense, flexible film that could accommodate thermal expansion and contraction without cracking. Chemical resistance to atmospheric pollutants, salt spray, and industrial acids made lead paint the premium protective coating for marine environments where other systems failed within years rather than decades. Application technique determined coating performance as much as chemical formulation. Brush application allowed paint to penetrate surface irregularities and bond with the substrate, while spray methods provided faster coverage but less penetration. The specification required brush application for the first coat to ensure maximum adhesion, followed by spray coats that built thickness efficiently while maintaining uniform coverage. Weather conditions affected every aspect of the sealing operation. High humidity prevented proper paint curing, while low temperatures made the red lead paste difficult to work and reduced paint flow characteristics. Wind could contaminate wet paint surfaces with dust and debris, creating weak spots where corrosion could begin prematurely. The work crews monitored atmospheric conditions constantly, adjusting their techniques or suspending operations when conditions threatened coating quality. The cable cross-section revealed the systematic logic of Roebling's protective philosophy as each layer was applied. The galvanized structural wires provided sacrificial protection at the steel surface through zinc's electrochemical properties. The galvanized wrapping wire eliminated physical gaps where moisture could accumulate against structural elements. The red lead paste sealed microscopic voids and provided chemical resistance to corrosive compounds. The multiple paint coats created a weatherproof outer shell that shed water and resisted atmospheric attack. Quality control required constant vigilance as the protective layers accumulated. Paint thickness measurements verified that each coat met specification minimums without exceeding maximums that could cause adhesion problems. Visual inspection detected holidays, areas where coating coverage was incomplete, that required immediate repair before proceeding to the next layer. Adhesion tests confirmed that each layer bonded properly with the preceding surface. The economic implications of the protective system became clear as material and labor costs accumulated. The galvanized wrapping wire, red lead paste, and multiple paint coats represented significant additional expense compared to minimal protection schemes that other projects employed. But the mathematics of life cycle costs favored heavy initial protection over repeated maintenance and replacement cycles that would be required with thinner, cheaper systems. The cable began to resemble a sealed pressure vessel designed to exclude moisture and atmospheric contaminants from the galvanized steel within. The overlapping protective barriers created redundancy that could survive the failure of individual components while maintaining overall system integrity. Even if the outer paint developed cracks, the red lead paste would continue providing chemical resistance. Even if the paste deteriorated, the galvanized wrapping wire would maintain physical protection. Even if the wrapping wire corroded, the galvanized structural cable would sacrifice its zinc coating to protect the steel substrate. The systematic progression from individual wire protection to complete cable sealing represented American engineering doctrine translated into physical reality. Each specification reflected understanding of corrosion mechanisms and protective chemistry rather than tradition or convenience. The additional cost and complexity were justified by service life expectations measured in decades rather than years, creating infrastructure investment that would serve multiple generations without requiring premature replacement. The final paint coat gleamed in the afternoon sunlight as crews completed the protective envelope that would shield the structural cable from maritime exposure for the next century. The spiral wrapping wire disappeared beneath smooth, lead-based coatings that would shed rain and resist chemical attack from coal smoke and industrial pollutants. The Brooklyn Bridge cables had become sealed vessels containing protected steel that could outlast the careers of everyone involved in their construction. May the 24th, 1883. The morning sun illuminated a completed span that had survived every prediction of failure, every funding crisis, every technical challenge that critics had declared insurmountable. Washington Roebling stood at his Columbia Heights window, telescope trained on the bridge deck as the first official procession prepared to cross between Brooklyn and Manhattan. The wire fraud crisis, the caisson disease, the public skepticism about American engineering methods, all had been overcome through systematic adherence to specifications that prioritized protection over appearance, thickness over speed, decades over immediate gratification. The opening ceremony attracted dignitaries who had questioned the project's feasibility throughout its construction. European engineers who had dismissed American wire-spinning techniques now witnessed a suspension bridge that exceeded anything built on their continent. The galvanized cables, sealed beneath their protective wrapping and paint coats, carried loads that justified every additional ounce of zinc coating, every turn of spiral wire, every coat of lead-based paint that had been applied according to Roebling's uncompromising specifications. President Chester Arthur's carriage crossed first, followed by New York Governor Grover Cleveland and Brooklyn Mayor Seth Low, their passage demonstrating public confidence in engineering methods that had seemed radical when construction began. The deck remained steady under ceremonial loads that would be exceeded thousands of times by commercial traffic in the decades ahead. Each vehicle that crossed validated the mathematics of cable strength, wind resistance, and dynamic response that had been calculated before the first wire was spun. The crowd's enthusiasm reflected more than civic pride. It celebrated the vindication of American innovation over European tradition. The suspended span achieved what masonry arches couldn't match: clear passage for tall ships beneath, while providing direct connection between boroughs that had been separated by ferry schedules and weather delays. The engineering solution created economic possibilities that justified the unprecedented investment in protected steel wire and systematic construction methods. Abram Hewitt's dedicatory address captured the moment's significance without exaggerating the achievement. The bridge represented applied science rather than spectacular engineering, he declared, proof that American methods could deliver infrastructure that served public needs for generations rather than decades. The galvanized cables overhead embodied this philosophy. Their protection systems had been designed for service life measured in centuries, rather than the expedient timeline that governed most construction projects. The numerical vindication began accumulating immediately. Daily traffic loads confirmed the bridge's capacity to handle commercial and passenger service without the structural stress that had worried critics during construction. The cable system distributed loads according to the mathematical principles that Washington Roebling had defended against skeptics who preferred the proven performance of European stone bridges. American wire spinning technology delivered the strength and durability that specifications had promised. By 2013, the bridge had operated for 130 years without major cable replacement or structural modification. The galvanized wires continued carrying loads within their designed safety margins, their zinc coating still providing sacrificial protection, despite decades of exposure to salt spray, industrial pollutants, freeze-thaw cycles, and the atmospheric chemistry of a growing metropolis. The protective barriers installed during construction, wrapping wire, red lead paste, lead-based paint, had maintained the dry environment that kept corrosion rates within acceptable limits. The mechanism's success became clear through comparison with modern practice. Zinc loss rates in non-marine environments typically ranged from half a micrometer to 2 micrometers per year, meaning that 80 to 170 micrometer initial coatings could provide protection exceeding 100 years if other barriers remained intact. The thick galvanized coatings applied to Brooklyn Bridge wire, combined with the sealed environment created by wrapping and paint systems, had achieved corrosion rates at the low end of this range. Modern cable systems demonstrated the consequences of different protective philosophies. Thin galvanized coatings measuring 25 micrometers could experience 50% zinc loss within 20 to 25 years when protective seals failed and moisture reached the coated surfaces. Contemporary wrapping wire often carried Class A galvanizing at approximately 0.6 of an ounce per square foot, roughly 1 mil thick, compared to the multi-ounce coatings and thicker barriers that 1870s specifications had required. The economic mathematics favored heavy initial protection over repeated maintenance cycles. Modern systems that prioritized low initial costs through thin coatings and minimal sealing often required major rehabilitation within 25 years. Consuming resources that exceeded the additional expense of thicker protection applied during original construction. The Brooklyn Bridge cables had avoided this cycle through specifications that treated protection as investment rather than expense. Advanced systems like wax-filled parallel wire strand and dehumidification technology could achieve excellent performance when properly maintained, but they required ongoing operational attention that the Brooklyn Bridge's sealed cables didn't demand. The passive protection provided by sacrificial zinc, multiple barriers, and systematic sealing continued working without pumps, monitoring systems, or regular intervention that modern active protection methods required. The urban environment had become more corrosive since 1883, with industrial pollution, road salt application, and atmospheric chemistry changes that increased the challenge of protecting steel infrastructure. Yet the Brooklyn Bridge cables continued performing within their design parameters, their thick galvanized coatings and sealed environment, providing margins that compensated for conditions more severe than their designers had anticipated. By 2023, the bridge approached its 140th anniversary while carrying traffic loads that exceeded original design expectations. The cable system continued distributing these loads safely, its galvanized wires maintaining structural integrity despite 4 decades of exposure beyond the century mark that had seemed optimistic when construction began. The achievement validated every specification, every additional cost, every delay that had been required to implement protective systems properly. The contrast with contemporary construction revealed the consequences of different engineering philosophies. Projects that chase speed and cost reduction through thin coatings, minimal sealing, and abbreviated curing times often delivered infrastructure that required major maintenance or replacement within decades rather than centuries. The mathematics remained unchanged. Zinc thickness, barrier integrity, and systematic sealing determined service life more reliably than promises or certificates. Washington Roebling's vision had become reality through specifications that measured what mattered: coating thickness, sealing effectiveness, and protection duration. The American engineering approach that critics had dismissed as wasteful had delivered infrastructure that served multiple generations without requiring the replacement cycles that consumed resources and disrupted commerce. The Brooklyn Bridge cables stood as proof that innovation succeeded when vision became specification, and specification enforced the discipline that transformed temporary expedients into permanent achievements. The numbers didn't rust. The thick galvanized coatings, systematic barriers, and sealed environment continued protecting steel wire according to the electrochemical principles that had governed their design. American ingenuity had won through measurement rather than hope, thickness rather than promises, decades rather than convenience.